So if you have more questions, please write them in the poll in the application, and we'll also have some time at the end of the session to come back to questions for all the talks. So now it's my pleasure to introduce our second speaker, Christophe Grova, who is a professor in the physics department at Concordia University, and Christophe will present data on simultaneous use of EEG and fNIRS as a new tool to investigate sleep in healthy adults.
Thanks a lot, Tan, for the introduction, and it's my pleasure to be here, and I'm very excited to show you for the first time this quite new result of using a new modality, fNIRS, to study sleep. So we'll see probably in the next talk, and Tan mentioned at the beginning, simultaneous EEG fMRI has been used quite a lot in the context of studying sleep, and we have some great results. For instance, this result by the group of Tononi and Melanie Boley showing during a nap some very specific spectral signatures occurring either during N2 with a peak lower than 0.1 hertz or higher peak more than 0.1 hertz during N2 and N3. Might be linked to slow wave, but probably also respiration. Few other important studies. We've heard a lot about slow fluctuation in the Bold signal, also in the global signal, as in a nice session yesterday. This is a nice study from the group of Laura Leris, linking this to what we heard earlier today about the flux of CSF to clean the waste in the brain during sleep, and this is linked to slow wave. So lots of cool stuff about EEG fMRI and sleep, but EEG fMRI is not that easy. It's complex protocol to study sleep. First of all, it's a noisy environment, so difficult to fall asleep. You need strict immobility. Most of the studies have been short duration, so most of the study have been following sleep deprivation or after or nap studies. And this is why I want to bring fNIRS as a more realistic technique to study sleep, and I will explain in a minute. I just wanted to mention that so far there are not so much fNIRS published studies on sleep. There are few, mainly linked to few sensors placed on the forehead, as in this study by Nasi, showing the change in hemodynamic response, oxy and deoxyhemoglobin during sleep transition stage. And in that study, showing also different spectral components in different sleep-specific stage, but again, just on forehead sensors. So why using fNIRS? So first of all, I'm going to recap a little bit. We had a nice session of fNIRS yesterday, but I'm going to just re-explain a little bit because it's less known. So it's a non-invasive technique that allows to shine light on your brain. So it's using two wavelengths, and it's going to be used to monitor non-invasively cortical fluctuation of oxy and deoxyhemoglobin with good temporal resolution. So basically, we emit near infrared light. Light will diffuse, will scatter in any direction. And if we place a sensor 3 centimeters around, the light will follow this banana shape here. And we're going to be able to explore roughly 1 centimeter depth of cortex. So we're not going deep. It's a cortical measurement. And the light is following this banana shape. What's going on when you have an activity? So hemoglobin will absorb light. Of course, if you have activity change, as in fMRI, you're going to have change in absorption. And because in the near infrared spectrum, we have mainly two absorbers, which are oxy and deoxyhemoglobin, by sending two wavelengths, we're able, by inversing Beer-Lambert law, we're able to reconstruct the local fluctuation of oxy and deoxyhemoglobin. And that's what we're going to talk about. So I just wanted to mention this software package that we put together. The paper is just out in Neurophotonics. So this is our package called NearStorm that is available as a fNIRS plugin for Brainstorm, just featuring what we developed for fNIRS. And I'm going to illustrate that in our sleep studies. So first of all, we developed what we call optimal montage. So we cannot put, we don't have high density fNIRS as shown yesterday. So when we want to target few regions, we have an algorithm to place the source and detectors in an optimal manner to target those regions, while allowing local density to allow 3D reconstruction. We have standard fNIRS processing, like filtering, averaging to compute the response, a little bit like you would do an ERP studies in EEG or MEG. And I'm coming from the world of EEG, MEG source imaging, so we also adapted source reconstruction or 3D reconstruction technique for fNIRS. And just to give you an example on a finger tapping task, this is the motor area we are targeting. This is our optimal montage with 3 sources and a bunch of detectors around it. And here we've been gluing the sensor with collodion on the head. And this is very important to have good signal during sleep. And just as an example, this was a finger tapping task with the fMRI response here. And after our method reconstruction, you see the increased oxy and the decreased deoxyhemoglobin. And you have more subject here. So now let's go to sleep. So this is our protocol. So first we start by an interview. So as usual, it's young, healthy subject, 18 to 35 years old, no medical conditions. And when they pass the interview, we ask for a control night. So it's a standard polysomnography night with electroencephalography, EOG, ECG, some measurements of muscle activity, and pulse plethysmography, and respiration. So quite standard. This is mainly to say whether their sleep quality is normal within those subjects. And then we go in MRI sessions because we're going to target specific regions, and we're going to target bilateral frontal and bilateral parietal regions for this study, because we know also that these are very important regions for spindle and slow wave during sleep. So this was our first target, and we develop our optimal montage during those. So this is subject specific, and then we use a neuronavigation, a brain-side neuronavigation system, to place the optodes and to glue them there. And we do that with standard polysomnography. So we are measuring fNIRS plus EEG plus muscle activity, respiration, plethysmography, arterial pressure, and so on. So this is where the 4 regions that we've been targeting for our optimal montage. And this is a montage that involves for each of those patches 2 sources and 4 detectors, and actually also additional short distance detector. And so if I look using Monte Carlo simulations of photon travel, this is the brain regions, the sensitivity to the brain regions we have for this montage. And once we have those positions here, to make sure we maintain those positions during the whole night and we have good quality, we've been using those very low profile fibers, and we've been gluing them with collodion. So it's quite intense in terms of preparing the scan, but at the end of the day, we get excellent data quality throughout the whole night. So we acquire almost 17 subjects right now. I'm going to show you results for the 13 first, 6 females, average age 24, and we get a very good sleep efficiency. After the first control night, all our participants were at a sleep efficiency of 90%. And our mean duration recording for all of those was 8 hours. So we use brain-side ROG research, so a wired fNIRS device with electrodes glue, plus 19 EEG electrode, and systemic physiology measuring arterial pressure, respiratory, pulse plethysmography. So this is our standard analysis, rapidly. So first, we looked at the EEG. So Dr. Peter Derex is a sleep neurologist who marked all the sleep stages and the sleep-specific information for us. And then we apply standard fNIRS pre-processing, batch channel motion correction, batch channel rejection. We converted optical density into oxyhemoglobin, filtering, short distance regression. This is to make sure we are measuring mainly activity from the brain and not from the superficial regions, because our light, of course, is going through the skin and the muscles before reaching the brain. So then we did time frequency analysis. So on this 8 hours data, we use Morse wavelet to look really at the oscillatory component. So we use some level of normalizations to remove the aperiodic signal, so to remove the 1/f, and to look at the peak of oscillation during this long data. And so then we average to get porous spectra in different stable sleep stages, so N1, N2, N3, and REM sleep as well. And also we did a linear mixed effect model to compare the activity in the different sleep stage compared to the awake state. So these are our results. So I'm going to show you here one first subject, as you can see. Oh, yeah. Okay, here we are. So here you have the hypnogram, where you see you go from N1, N2, N3 sleep, and then REM sleep. And here you have the time frequency of oxyhemoglobin in the frontal and parietal regions. And then the pulse plethysmography, the respiratory bell, and the arterial pressure. And what was very striking here is you see that when you are in deep sleep, in N3, you have almost no activity besides the respiration part. Whereas in some other stage, we get very low frequency that were around 0.01 hertz, for instance. So quite lower from what was reported with fMRI. And of course, in fMRI, you might not get those very low frequency because of fluctuations of the signal. This is just to show you variability. So these are 4 different subjects, and you see again the same patterns. When you go in N3, it's almost switching off everything except respiration, and in N2 or in REM, you have some interesting low frequency component. If we try to summarize that, this is the summary for frontal and parietal regions for awake, N1, N2, N3, and REM sleep. And you see that N2 and N3, we see mainly activity in the respiration band, around 0.2, whereas in REM, and again here, we see some activity around here. When we see the plethysmography and the respiration band, we gain mainly respiratory activity, or in plethysmography, it's cut here because it goes to 0.5 hertz here. So we have the cardiac. And in the arterial pressure, we get a peak at 0.1 hertz, which are the famous Mayer wave, which is also linked to the very close to our standard hemodynamic response. So when I want to compare that, this is what I'm getting. So here I'm doing the comparison between the different states to the awake states, and I see a significant increase in my linear mixed effect model in the respiratory band. So I see an increase in N2, N3, and N1 compared to awake, and I see a decrease of activity around 0.01 here. And I do see an increased activity in those very low band, specifically for REM sleep. This is about the same for parietal. We see a little bit less. And then just in the last minute, I wanted to confirm. So these were the group result on the channel level for our 13 subject. And then we wanted to do a bit better to go into the cortical surface. So fNIRS is a scalp measurement. Can I invert the system to go along the cortical surface as I would do for EEG or MEG source imaging? So this was a proof of concept that showing that we did that not during average signal, but during ongoing signal. So here you have 80 minutes of finger tapping. And after doing that, we get, with our technique called wavelet maximum entropy on the mean, we get a very nice reconstruction here. And if I look on this finger tapping, the power spectra, you see the cardiac here, the respiration here, and some low frequency activity here. This is at the channel level, and this is in the source space or on the cortical surface with standard technique like minimum norm and with our technique. And you see that our technique is enhancing quite well those very low component of interest. And I would like to illustrate that. What you see here, for instance, is some ongoing activity that has been measured. So this is only one subject for the moment. This is 10 minutes of N2 sleep oscillations using oxy and deoxyhemoglobin. And this is, and here you see that it's an N2 signal with some spindle activity, as you can see here. This is the same for N3, showing slow wave activity. So you don't see the slow wave because it's compressed. Here you have 10 minutes of signal. And you just zoom on the signal, you see slow wave activity. So if I look at that, you see that now this is my hypnogram. So this is very new. We got those results like 2 days ago. And this is the time frequency analysis on the channel level and after 3D reconstruction. And you see that we enhanced quite well those very low bands. So this is very promising in looking at those bands. And this is my last slide, showing that here we see that, of course, we have those peak of activity in the different bands, mainly in N3 during around respiration bands, so 0.2, but around 0.01, and up to 0.05 and even before, we have different peaks, and including a very strong peak in N2 notably, and very less activity in N3, and we have broader activity in REM. So this is only one subject, but this is in agreement with what we see on the scalp, and we look forward to develop all that. So if I want to conclude on that, we show that personalized EEG fNIRS looks like a new tool to investigate sleep. It's complementary to EEG fMRI. It's more naturalistic way. There is no noise. You can sleep well. And it allows all-night recording. We got similar spectra as in fMRI, but we were able to assess lower frequency, like 0.05 to 0.01 hertz notably, which are difficult to get in fMRI. I did not show, but we got very specific signatures in REM phasic and tonic states, because it's very difficult to get REM sleep in fMRI. We were able to do it through our night. And our 3D reconstruction using wavelet MEM seems to enhance the contrast, as we have already demonstrated in MEG. So as perspective, we want to assess also the sleep microstructure. What's the fNIRS response to spindle, slow wave, REM phasic, tonic? The methodology is ready when we'll have an high-density fNIRS with low-profile sensors that we can use, and we are looking forward to do that. And I'd like to, if there are people interested in joining us in that project, it's only starting, but I would like to build a normative atlas of sleep physiology using fNIRS. So if other teams want to join us on that, I would be happy. And then we would like to use that to compare with sleep pathology. And I'd like to thank my collaborator. Thank you very much.